Today we want to take all this integration that we've been working on. We've been working on building triple integrals in various kinds of coordinates. What we want to do today is connect this integration thinking to old ideas, what we already have thought about as far as integration goes. Because a lot of times you start digging into mechanics and doing specific problems, and you start to forget what you're actually doing. So let's connect our integration with triple integrals to old ideas. Let's review the way we think about integration. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. It's the continuous part that makes it interesting for us. What we do is we take our continuously variable factor and we assume that it's going to be constant for small changes. And we're going to reframe this problem in a single function, a single variable function. We're assuming that the value of the function is constant for some small change in x. That means we can multiply. Once we have constants, we get to multiply. Once we can multiply, we multiply and then add up all of the products over all of the subdivisions. Then we let the number of products go to infinity. This is where our discrete sum becomes a continuous sum in the definite integral. So here's the Riemann sum and the thinking behind it. And then we get the integral. In the integral, we got to remember what we're calculating is f of x times dx. And we're doing this continuously for all the values of f of x, all the values of x from a to b. The integration part is telling you what values of x to plug into f of x dx. So we calculate f of x dx for all the values of x. The integral is saying plug these numbers into the f of x dx. And this is generalizable. If we have, instead of an f of x dx, we have an f of xy times dA. We're just going to evaluate that at all the points in the region. So upgrading this, when we think of calculating for all these values, when we upgrade this to, let's say, the integral over r of f of xy dA, we're going to calculate f of xy times dA for all the values xy in the region R. So it's the same kind of thinking. This is what we're calculating. We evaluate the function at a point, multiply by the dA. We're calculating f of xy dot dA, or times dA, for all the points xy in the region R. Then we add up the results. So we're thinking about our multiplication problem in terms of addition. We can think of multiplication as fast addition. If I want to add up the total number of points earned in the class, if y'all would be real so kind as to just get the same number of points on everything, then I can get the total number of points by saying 10 points times 18 people. but we're not all gonna get the same score on things. So I'm gonna say 7 people got 10. 6 people got 9, and so on. So I can break it down and I have to add up the products when the factors are different. Now, fortunately, we teach in a nice continuous, a discrete class. So there's one student, then the next student, then the next student. There is a next student. In the continuous classroom, there is no next student, and we have to integrate to get the total number of points. Any questions? Comments? And we can do this same thing with dv. I'll just write f at x, y, z times dv. And we add up all the points x, y, z in the solid w. We calculate f at x, y, z times dv. At all the points x, y, z in the solid w, and they were imagining adding those values together. This is how we want to visualize integration in general. Our ways into this are area under a curve, volume under a surface, and we don't really have one for dv because it's a 4-dimensional volume under some 3-dimensional solid and above the XYZ plane. So it's a little hard to picture. Mechanically, what we're doing is we're evaluating the function times dA or dV or dx at all the points listed in the integral part. Any questions? All right. Let's keep connecting our new ideas to old ideas with a progression of problems. Let's suppose we have a rectangle, 0 to 5 on the x and 0 to 3 in the y, and the density of the rectangle is a constant 2 grams per square centimeter. And we want to find the mass and we want to find the mass of the rectangle. This is going to be based on multiplication. The mass is going to be the density multiplied by the area. Mass is going to be the density times the area. Since I have the length and the width and it's just a rectangle, the mass is going to be the density multiplied by the length multiplied by the width. Wrong color. All these quantities are constants. The density is always 2 grams per square centimeter. The length is just 5, I'm going to call it 3 centimeters. And the width is 5 centimeters. When we multiply, we get 30. The 2 centimeters cancel out, centimeter squared. The 2 centimeters cancel out, and we're left with grams. Because all these factors were constant, all we had to do was multiply. All the factors are constant, so we just need to multiply. All the factors are constant, so we get to multiply. We get the simplest version of the problem. Any questions? So now we're going to turn it into a calculus problem by changing one of these constant factors to a variable factor. So let's go with the same rectangle. But density at any point x units through x centimeters from the y-axis is 1 plus 0.4 grams per square centimeter. So now we don't get to multiply because our density is variable. So variable density, we don't get to multiply. There's a variable factor, so no multiplication for us. So we're going to do the same thing that we always do. We assume that the density is going to be constant for some small change in x. Let's draw a picture about what that looks like. So here's our rectangle going from 3 to 5. Yes. 0.4x. Yes, I did. Whoa. Thank you. Otherwise, it's still constant. We're still going to set up mass is density times length times width. So density times area. So we're going to still set up mass is equal to density times length times width. We're just going to have to do this in pieces because our density is variable. So at some point, x units from the y-axis, my density is constant. So I'm going to mark where the density is constant. So the density at this point is 1 plus 0.4 xi. So just at that point, I want to use this density for some small change in x. Now I need to make an area over which I'm going to use that approximation. So here's my small change in x. There's my width. And my length is constant at 3. So our density at this point is 1 plus 0.4 xi. Our length at this point is a 3 always. And our width is the delta variable, delta x. Now we just add up all these, the masses of all these rectangles, and that becomes our definite integral. I'm going to factor out the 3. And we're going to integrate the density. Our discrete xi becomes a continuous x. Our discrete delta x becomes a continuous dx. And now instead of counting the number of rectangles, sum as I goes from 1 to n, counting the number of rectangles, we're plugging in all the x values. We're going to make this calculation at all the x values listed in the integral. And we'll start the x values at 0 and end at 5. So x equals 0 to x equals 5. And this will give us some number of grams. Out of the 3 factors, one of them was variable. The density was continuously variable, so we had to switch to integration. Before, when everything was constant, we got away with multiplication. In between, we could have had a discrete sum. If I said the density from x equals 0 to x equals 2 was 3 grams per square centimeter. And then the density from x equals 2 to x equals 5 was 7 grams per square centimeter. I would be able to do the multiplication where the 2 densities are constant, and then I would add those 2 together. We're doing that same thing, just with an infinite number of rectangles, because our density is continuously changing. Any questions? Now I want to change things a little bit more. I'm going to take not the same rectangle, but I'm going to take the same density, but I'm going to cut the rectangle down. So same density. Same density, but we're going to have a triangle. The triangle is still going to be I'm just going to carve the triangle out of so I want this upper triangle. And same problem. We want to calculate the mass of this triangle. We have to look at how the density is variable. The density is variable moving from left to right. But we're still going to calculate mass is density times area. And area is still going to be length times width. We're going to do the same thing we did last time. I'm going to pick a place where the density is constant. So I'm going to pick a point xi units from the y-axis. And I'm going to calculate the mass if I keep this density constant for some small change in x. So in this case, the length is not a constant 3. So now the density is variable and the length is variable. Our width is still our delta variable, delta x. Our density is still just the density 1 plus 0.4x. But now our length is variable. So when x is equal to 0, the length is equal to 0. When x is equal to 5, the length has increased to 3. So we can just make a linear function where the length starts off at 0 when x is starts off at 0 when x is 0 and increases by 3 over 5 units. When x is 0, the length is 0. When x is 5, the length should be 3. So that means we start off at 0 and increase by 3/5 times xi. In this case, we were able to get away with just making a linear function because we could see that this is going to be a linear function. if one of these was wobbly and not so linear, we might think, shouldn't this look like the top function minus the bottom function? And it does. So the top function up here is y equals 3. And the bottom function down here is y equals 3 minus 3/5 x. So if I set the length up as the top function minus the bottom function, I would write 3 minus the quantity 3 minus 3/5 x. So our length is still going to be 3/5 xi. So our density is the 1 plus the 0.4 xi. Our length is 3/5 xi. And our width is the delta x. So this is going to become an integral. We add up all such products. And we'll have the integral of, I'm going to factor the 3/5 out. Then I have an x times a 1 plus 0.4 x. We drop the indexing because we've gone from the discrete to the continuous, and our discrete delta x becomes a continuous dx. We add up all these values nice and continuously, and we'll get some number of grams. Any questions? Comments? So the rectangle has a mass of 30 grams. And then for my triangle, I'll do 3/5. Still 0 to 5. And we get 17.5. Because this problem has context, we have essentially a word problem, the answer should make sense. So if I look at what I'm trying to calculate and how these two problems are related, the area of the bottom triangle is half the area of the rectangle. But the density wasn't constant. So we got to think, does it make sense that we have more than half the mass in this upper triangle? And since the heavier part of the rectangle is here where x is equal to 5, the upper triangle has more of the heavy end of the rectangle. So it makes sense that the upper triangle should have more mass, more than half the mass of the rectangle. Any questions? Is everybody okay? So let's think about the same triangle. Keep that's the same, but now adjust our density. So the density is now no longer going left to right. The density is going from top to bottom. So now our triangle So the difference in this problem, I still have a variable density. And we still want to calculate mass as density times area. And so that's still going to be density times length times width. But in this case, the density is not changing side to side. The density is changing up and down. The density changes with y, the distance from the x-axis. So now my density is going to be calculated here. So now my width is going to also be variable. So here's where my density is constant. And I'm just going to use that same density for some small change in y. Questions? Then we just have to do the same things that we did before. Write the length as a function of y. So when y is equal to 0, the length is equal to 0. And the length will increase by 5. So when y gets to 3. So increase by 5 every 3 units. This is the same thing that we would get if we did left, the right minus the left. Just the same as top and bottom in the previous example. And so now we're ready to plug our 3 parts in. The density is 1 plus 0.4 y. The length is 5/3 y. And the width is, oops, I switched these around. I don't know if this is a more coffee problem or a less coffee problem. I just know which solution I'm going to apply. Our width Our length is the delta y. And our width is 5/3 y. Now we just need to add up all these values for all the different values, of y. In the Riemann sum, we're using an infinite number of rectangles, slices that look like this. The definite integral, we're adding up the length times width times density for all the values of y. So I'm going to factor out the 5/3. So I have 5/3 times y times my density times my length. We're going to add up over all the values of y, where we see these densities, and the values of y go from 0 up to 3. So we integrate from 0 to 3. We're going to get a different value than we had in the previous one because this is a different triangle. So we're not looking for the same value as I've changed how the density is defined. Any questions? And this will give us a mass in grams. In each of these problems, the density was only varying in one direction. So if we take the same triangle and change the density, instead of being just a function of x or a function of y, the next evolution of the problem is same triangle. Same triangle, but we'll make the density f of xy a function of two variables. Same triangle, but now I'm making the density not dependent on just x or just y. We're bringing this problem finally, last 5 minutes of class, finally into the Calc 3 realm. And the problem changes radically because the mass is going to be the density times the area. Oh, I guess it's not changing at all. And that's still going to be the density times the length. Still going to be density times length times width. The difference is that our density is a function of two variables. Our density is a function is f of x and y. That means our length and our width are going to be deltas. So the length is going to be the delta y, and the width will be the delta x. And together, these two will combine to make the delta A. We can also set this up as an f of x, y, delta x, delta y. But we're going to do the same thing. We're going to evaluate f of xy times dA at all the points in this triangle. Now we just have to describe that triangle to a double integral and actually write a value for the density. Any questions? Comments? Thoughts? How's everybody think? The important thing to think about is that integration is multiplication, but one of the factors is variable. So if you're looking for applications of integration, just start by looking at all the different applications of multiplication. I think, what does it mean to make one or more of these factors variable? Is everybody okay? I know it seems like a lot of almost the same problem, but asking 10 problems just randomly selected is less effective than just asking 5 problems in a sequence. One of the reasons that it's better is that it uses 2 derivatives. We're not just looking at problems where they are, but we're thinking about what direction things are going. We're thinking about location, f of x, and we're thinking about direction, f prime of x. So we're looking at the differences in these problems. That's where the interesting part comes in. Is everybody okay? All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.